Okay, this is our last installment in our titration lessons. And in this example, we're going to be reacting a strong acid with a weak base. And so in this case, the strong acid, when added to the weak base, is going to convert that into its conjugate acid. So we're going to have our weak base, right, our B, and for every mole of that HCl that's added to the B, it will be converted into its HB plus, its conjugate base. And it's going to be, just as before, the concentrations of this base versus the concentration of its conjugate acid that's going to determine the pH in the Erlenmeyer flask. So just like our last example, I need to take note of some volumes: volume of the acid, concentration of the acid, number of moles of the acid, and volume of the base, concentration of the base, and the number of moles of base. And we've already did a derivation to determine the concentration of the weak acid. And it will be the same derivation that will get us the concentration of the weak base that's left after the titration. Recall that for every mole of the acid that's added to the base, that base will decline. That base will go down because it's going to be converted into the number of moles of the conjugate base. So to figure out how much base is left, I need to take the number of moles of base that I started with and subtract the number of moles of acid, because it's consuming it. The volume, just like before, VA plus VB. To determine the concentration of the conjugate base that's created, again, for every mole of that acid, it's going to convert it directly into moles of conjugate base. So if I have the number of moles of acid that I added, and I divide that by the new volume, I will have the concentration of the conjugate acid. And depending on what's in the water and how much base versus conjugate acid is going to determine the pH, just like in the acid example. So let's go through some examples here. So right at the start, again, I'm going to write down my acid, strong acid, the weak base. I'm going to get some data down. I'm not really concerned about the products because I really just want to get my numbers in order. I'm dealing this time with 10 milliliters of NH3. Its concentration is 0.25 moles per liter. And again, just like with the last one, C equals N over V is going to guide us on how to determine the number of moles, in this case millimoles. And if I multiply these two together, I'm going to get my 2.5 millimoles of the base. And at the beginning, there is no acid added. Concentration might be 0.20 molar or moles per liter, but it doesn't matter because there are no moles of the acid left. Now, I could use that equation again to determine what the concentration of the base is at this point, but we did this calculation last time. In the end, when I do the calculation, I'm going to get my original concentration back, and that's because I haven't added any acid. That's exactly how much base I have. So I have 0.25 moles per liter of the base. Conjugate acid, well, no acid has been added to convert into the conjugate acid, 0. So what does that make this? Well, with only base in the water, this is simply a weak base problem, which means the OH concentration will be equal to the Kb times the concentration of B. Now it turns out that for NH3, the Kb is 1.8 times 10 to the minus 5. And if you think that looks familiar, that is also the same as the Ka for acetic acid. even though that's a coincidence. That is not a relationship. Multiply that by 0.25, our original concentration. We end up with 0.00212 moles per liter. Taking the negative log means I'll get a POH. The POH is 2.67. And subtracting from 14, I'm going to get a pH of 11.33. All right? So it's basic. Well, of course it's basic. It's a base. So let's now proceed through to the next situation. Now, hopefully, it's getting very repetitive. HCl, NH3, 10 milliliters, 0.25 moles per liter, 2.5 millimoles. In this case, I've added 3.0 milliliters, 0.20 moles per liter. And if I multiply those together, I get 0.60 millimoles of acid. So how much base is left? HB. Sorry, that should just be B. How much base is left? Well, we've consumed 0.6 millimole. So 2.5 millimole minus 0.6 millimole is how much base is left. And that's over 13 milliliters. And if I do that calculation, I get 0.146 moles per liter. And so how much conjugate acid has been made? Now remember, because we have added that H onto that thing, we're going to get some NH4 and H4 plus, which is the conjugate acid. And for every 1 mole of HCl, I will get 1 mole of the conjugate acid. And so I'm going to have 0.60 millimoles over 13.0 milliliters. And if I do that calculation, I'm going to get 0.0462 moles per liter. Notice here I have both the base and its conjugate acid. This again is a buffer scenario. All right? So I need my base buffer equation. OH, KB, B over the conjugate acid, 1.8 times 10 to the minus 5. The B, 0.146. The HB, 0.0462. And if you do that calculation, you will find, hopefully you'll find, because I don't know, I hope I did these right, 5.69 times 10 to the minus 5 moles per liter. Again, if I take the negative log, POH is going to be 4.25, and pH is going to be 9.75. 9.75, all right? Still basic. Okay, so let's now proceed on to the equivalence point. Remember, at the equivalence point, the number of the moles of acid equals the number of moles of base. HCl plus NH3, 10 milliliters, 0.25 moles per liter, 2.5 millimoles. Now, because we're at the equivalence point, 2.5 millimoles, 0.2 moles per liter. And now I'll work my way up and solve for the volume. 12.5 milliliters is needed. Okay, so at the equivalence point, my B, well, because I have equal numbers of moles, all of the acid has consumed all of the base. There's none left. It's all consumed, 2.5 minus 2.5. And my conjugate acid, it's all been converted. 2.5 millimole. That's now found in 22.5, right? 10 plus 12.5, 22.5 milliliters. And if we do that calculation, we're going to get 0.111 moles per liter. So again, notice at the equivalence point, this is all weak acid. I'm going to determine the pH this time using a weak acid equation, Ka, and that's of the conjugate acid. And in this case, the acid is our Hb+. It's the conjugate acid of our base that we started with. The Ka for the conjugate acid, 5.6 times 10 to the minus 10. I got that off of the table for NH4+, right? And H4+, that's the conjugate acid, times 0.111. Take the square root, and that gets me 7.88 times 10 to the minus 6 moles per liter. And I can take the negative log directly of that, and I get a pH of 5.10. Notice at the equivalence point, for a strong acid and a weak base, that thing right there is less than 7. All right? That is smaller than 7. Okay? All right, which means we have an acidic equivalence point. Excellent. Halfway to the equivalence point. We're going back the other way. Now, I don't know if you recall, but at halfway to the equivalence point, at halfway to the equivalence point, we found in the last one that the concentration of the acid and its conjugate base were equal, and that's also true here. At halfway, we've converted exactly half of the weak acid into its conjugate base. It is still a buffer scenario, but it is a weak base buffer, OH, Kb. I'm going to have the base over the weak conjugate acid. And because they're equal, they cancel out. So, again, a very useful point. Halfway to the equivalence point, the OH is equal to the Kb. We're talking about the Kb of our NH3. And the Kb, remember, is 1.8 times 10 to the minus 5 moles per liter. That's how much OH there is. That means we can directly get the POH, 4.74, and the pH, which is 9.26. All right? Okay? Okay, that's exciting. Again, that's a method in which we can get the KBs. If we can do a titration and find the POH at halfway to the equivalence point, then that pH converted to H3O+ will tell us the Kb. A good shortcut to remember. And now let's do the last part where we blow right past the equivalence point, where we've got excess acid, HCl plus NH3. This time I've got, again, 10 milliliters. That's what I started with. 0.25 molar, 2.5 millimoles. And this time I got 20 milliliters, 0.20 moles per liter. And if I do that multiplication, I get 4.0 millimoles. And you can see I have an excess of acid. The number of moles of acid is greater than the number of moles of base. I've gone past the equivalence point. Past equivalence point. Okay? That means all the weak base is consumed. We have an excess of HCl. And this will determine the pH of the solution. So the concentration of our HCl at this point. We started with 4.0 millimoles of that acid, and 2.5 of it was consumed by the weak base. That's going to now be in 30 milliliters of water. And if I do that calculation, I'm going to get 0.050, actually another significant digit likely, but that's not too bad. No, the concentrations are only 2, and that's moles per liter. And that means the H3O plus, because it's a strong acid, is also 0.050 moles per liter. And if I know the H3O plus, I can take the negative log and I can easily get the pH, which is 1.30. All right. So really, when we do our titration questions, it's really thinking about what is consuming what, whether I have weak acid or weak base or a combination of two in the solution. And after the equivalence point, the pH is determined by the strong substance, whether it's an acid or a base. Let's take a look at the titration curve. It's not shown in the same detail here, but on this curve as well, I would have a buffer zone, all right? There'd be this buffer zone. And again, at the halfway to the equivalence point, my equivalence point 20, at 10, if we could take that pH right there, that pH, we could ultimately turn it into a pOH, and we could get the Kb. Again, notice the position of the equivalence point. The position of the equivalence point is now acidic because I have the weak conjugate acid. So the weak acid is in the water at the equivalence point, which means we would need an indicator that changes color somewhere between 5 and 6. And you can see there, if we had our big table, methyl red would be a good choice. All right? And it would be tough to see between red and or yellow. We would be looking at an orange in there. It'd be an interesting one. Okay, let's do a quick summary at this point. Now, this is an example that I would have done with you during class, but you can write it down. You can give it a try and check with your neighbors. You can pause the video if you need to. And again, just before I give you some homework, I just want to talk a little bit about a summary here. I'm going to bring the whole thing up here. So in this lesson, we've looked at 3 types of titrations: strong base added to a strong acid. Before the equivalence point, we didn't do the calculation, but because we're starting with the acid, because we're starting with the strong acid, we're going to be very much less than 7, all right? Halfway to the equivalence point for strong and strong, again, not important, simply less than 7. At the equivalence point, for strong and strong, right on 7. And past the equivalence point, because now we have more base in the water, we are definitely greater than 7. All right? Now taking a look at the strong base added to the weak acid. At any point before the equivalence point, we have these buffer scenarios. Buffers at any point before the equivalence point. That means, in this case, I have the weak acid, so I need the weak acid buffer H3O plus Ka HA over A minus. All right? And you'll notice that's going to have to be less than 7 because it's an acid buffer. At the equivalence point, we've got the super shortcut where the HA and the A minus cancel out. And so the H3O plus is the Ka. Again, less than 7. Now, at the equivalence point, we've turned it into all weak base. We've turned it into the conjugate base. So we need our base equation, OH minus root Kb, and in this case, it is the conjugate base of the acid. And notice the pH at the equivalence point is greater than 7. It is basic. Once we blow it over the top and add lots of base, it is also basic, greater than 7. Okay? And finally, we looked at strong acid added to a weak base. Again, we've got buffers. Anywhere before the equivalence point, except right at the beginning, where it's all weak base. We have buffers, and these are the base buffers. Kb, concentration of B over the conjugate acid of B. At the equivalence point, again, the B is equal to the HB. They cancel away. OH minus is equal to the Kb. That's the shortcut. Again, both of these are basic, greater than 7 pHs, greater than 7 pHs. At the equivalence point, we've turned it all into the weak conjugate acid. So I have an acid equation here, H3O plus, Ka. In this case, it is the conjugate acid of the base. So I will put Hb plus. And again, the special case here, at the equivalence point, you might think it should be neutral, but it is not. We have an acidic situation. We have a less than 7 pH, all right? And when we blow it over the top and add lots of acid, very much a pH of less than 7, all right? And if we're having trouble still with our greater thans and less thans, imagine that there's a pH in front of every one of these. I think it was you guys who struggled with that. Anyway, all right. There are some practice problems that deal solely with titrations. You can pause that to write that down. And finally, there are many, many practice problems that deal with our acid-base equilibriums, because now we are set for a unit test. And yeah, this is the last lesson before the unit test I would have discussed with you when that test would be.